I expect
She's in AP calculus. And it right in the middle. Okay, so I'm gonna re-say B because that was very rushed, and then we'll look at C. So for B, we wanted to know when the wind speed would have a wind chill of 0. So we set that middle equation equal to 0. -7 will never equal 0. 30 will never equal 0. So this is the only piece that could equal 0. Then we did quadratic formula. This is our A, our B, our C. And one side did plus, one side did minus, and we got these two numbers. However, the variables were different this time. It wasn't a quadratic. And normal quadratic formula is x equals based on this middle term. So this time, since the middle term was square root of v, that's what those answers give us. And then if we want v, we need to square each of those to get v. Okay, but now, so many buts. The conditions, the domain for v is this middle piece only works when it's between 4 and 45. So this is out. So then our magic answer is when the wind speed is 25.3274 miles per hour, we'll have a 0 degree wind chill. And that's kind of where we rush to end. Questions on that part before we look at the last part on C. Okay, now C is where we get into this continuity stuff that 1.4 has been about. We want to know if it's continuous at 4 and 45. So that's where the pieces are joining up. So we've got 3 little pieces. Do they connect? Are they continuous? So what we're first going to do is check, does this piece connect to this piece? Well, they're meeting up when the V value is 4. This is always going to be 30. So we need to put a 4 into this equation and see what it gets. So why don't we try that out? Put 4 in for V. And we'll see what value we get out there. May be quite interesting. It only goes to the hundredth, so we won't have to worry about rounding. What do we think? 29.96. So this is giving us a y value of 29.96. Are those pieces meeting up and continuous? No, so close. But no, if you're out in space and you say, we want to attach the hose into the port, but it's 0.04 hundredths off, I'm not going. You want it to be exactly. So they're so close. It's a little itty bitty jump. One's coming in at 29.96 and one's coming in at 30. So almost, if you looked from far away, it would look continuous, but not continuous. Okay, let's check the other pieces. Let's check this piece, if it will meet up with this piece. So they're split up over the value 45. That's where the v value, the x value. So we're going to put a 45 in here now and see if it matches up with -7. Bless you. It does exist.
We were plugging in -7.
No, 45.
Oh.
45. Okay, this one we will have to round. Anybody want to share their answer on this one? Megan? -6 point. Okay. Oh my goodness. Can we count it? No. It's close, but not quite. And when they created this model. So they did a pretty good job at making it seem almost continuous. But when we have to go and answer this question, is it continuous at 4? No. Is it continuous here? No. They're little jumps, so it would look pretty decent, but they're not quite continuous. And so that's a jump. Do we remember what type of discontinuity jump goes with? Non-removable. So our non-removable were jumps in vertical asymptotes, and then our removable were holes. So that's kind of where we're getting at with 1.4. Okay, now we're going to kind of put 1.4, give it a little rest for a little bit. We're going to go into 1.5 today, and then we'll get back to reviewing and everything. But 1.5 is not crazy. It's not very long. It does have a pretty good flow to it, and we'll get into that now. And what it's called is infinite limits. And we're going to be looking at limits from the right and the left again with this. And we're going to get really good at knowing how to see graphs in our head on this one. Okay, so we're going to base almost all of what we do in this section on this parent function. This is going to be our main focus. Okay, go ahead, take a moment and graph that in your calculator. So in your y equals, put 1 over x, so we can get an idea of what this parent function looks like. The calculus loves this function, so we're going to get to know this function a lot. They love to put this in examples. And we've got something going on like this, right? We can see that on our graph. So right there at 0, there's not a limit. Also, it's discontinuous. What kind of discontinuity? Non-removable. And what else is it called? Vertical asymptote. Okay, so now we're going to kind of combine that discontinuity we've been doing with limits. And I'm going to say this. We're going to take the limit of this function as x approaches 0 from the left. Yes, Connor.
I keep on going to graph and then it says that.
Okay, let's see. I'm going to turn your stat plots off. And let's see. That was it. I would just do Zoom 6. I did a weird Zoom But yeah, it's dot plots. Okay, now remember that little minus sign. We're looking at it from the left. So as we approach 0 from the left, do we feel comfortable right now saying it does not exist because it's going forever? Okay, well today we're just going to add a little bit onto that, and they like us to be specific about how it does not exist. And so what we're going to say is what direction it's approaching. And so as we come at it from the left, since it's going down forever, we're going to answer this negative infinity. So it does not exist, but it's a specific version of that. And so if you can answer an infinity answer, they want that over DNE. Like if you put DNE on this problem, they would say, we're not going to accept that. We want the specific case. Okay, let's look at this one. The limit as x approaches 0 from the right of the function. Okay, so as we're approaching from the right, no limit, it's going up forever. So then this is a positive infinity. And they'll get you, like I've seen it on like multiple choice questions. One choice will be positive infinity, one will be negative infinity, one will say does not exist, and they're trying to trap you. That's just all it is. Okay, then we're going to do the limit as x approaches 0 of the function. So when we don't have a certain direction, we have to look from both sides. Since these infinities are conflicting, then we can put DNE. So then that's when that's acceptable. So now we're tweaking our does not exist with this is what we're going to do. Okay, questions right there before we jump into some more of these. Okay, now what we're going to do, because this is fun, we're going to work on our transformations with this. Yay. Let me see this. Let me put the function first. So new example, our function is going to be 3 over x minus 4. No calculators. We're going to figure out what's going on here. So now we got to remember the pre-calc chapter on transformations. Okay, so 1 over x is our parent function. Does anybody remember, or they want to take a stab at, what x minus 4 is telling us? 4 to the right. And remember to get that direction, if you set this equal to 0, it would give you x equals 4. So that's positive, so that's why it's to the right. Does anybody remember what that 3 does? No? Honest answer? It's a scalar. It was the a term when you had it, and so it would like shrink it, condense it. I don't know what all the terms he used. Compress, stretch. It did all of that. Okay, well, that x minus 4 will help us kind of move it over. I do have some good news for you. Will stretching or shrinking affect my limit? No. So for these questions, the scalar isn't going to affect it, so we don't really have to worry about the scalar in these instances. So that's some good news. So what we're going to do, we're going to try to graph this. We're going to take our parent function, but we're going to move it to the right 4. So I'll go, and then it looks like this. So just a horizontal shift 4. Okay, now we're going to find the limits that go with that. So the limit as x approaches 4 from the left of f of x. So now on that red line, as we approach 4 from the left, what is the most accurate way to answer that? I like negative infinity better. Okay, now we're going to do the limit as x approaches 4 from the right of the function. Okay, so now that red line coming at it from the right, what's the most accurate answer? Infinity. And then you probably know the pattern by now. We're going to do the limit as x approaches 4 of the function. And what are we going to put for that? From both sides. Does not exist, DNE. Okay, so we're going to transform that. I got lots of transformations for us to do. Let's try this one next. Let's do the function 1 over 2 minus x. Okay, so there are a couple of ways to approach this. First of all, does anybody want to tell me what they think that 2 minus x might do to our graph? How might that affect our parent function? You're right about that. There is a flip going on. Anything else we know? Sophia? I like it. Okay, so I'm going to be working with this. Take out a negative. Oops. Take out a negative. So then it's kind of easier to see. When you take that negative out, get the terms in a more familiar order, we see that shift. But then that negative, mathematically, can't I put a negative anywhere on that fraction? I can move that negative. And when you have a negative a value, or it could be rearranged, that flips it. So what this is going to do, it's going to move it to the right 2 and reverse it, flip it. So what we'll see, I'm going to go to the right 2, and then instead of it looking like this, it looks like this. That's our reflection. Okay, then we're going to find some limits, practice our limits with this. The limit as x approaches 2 from the left of the function. So that blue line, as we're coming in from the left, what's the most accurate answer? Infinity. All right, you know what's coming. The limit as x approaches 2 from the right of the function. So come at it from the right-hand side. Answer? Okay, good. And then we want the overall limit, the true limit. The limit as x approaches 2. And what's that answer? There we go. Okay. Let me tweak this a little bit more. You're going to be able to graph some really complex things when you think about that, just that parent function. All right, next function. Let's do 2 over the binomial x minus 3 squared. Okay, now, maybe even as little as 5 minutes ago, if I told you you had to graph this because your life depended on it, you might just leave the room. But we're gonna show how it's easy now. Okay, so what's the x minus 3 do? To the right 3. What's the 2 in the numerator do? We don't care. What's the square do? What does a square do to numbers in general? Like if you take, it makes the number multiplied by itself. You are so correct. What does it do? Like, I don't want to say it without giving it away, but okay, that's going to be more like that 2 in the numerator. But yes, I see what you're saying. I see what you're saying, like a parabola. Yep, that's true. Andrew? It does deal with multiplicity also. It will go with how many zeros and that kind of thing. Yep. You guys are good. What does it do? Let me just say this. What does it do with a negative number? Makes it positive. Is there any negative number in this domain, in this range? There's never a way we can get a negative number, right? So it moves it to the right 3. I don't care about this 2. And then it makes everything positive. So then it shoots them both up. So that's what our graph's going to look like. I know. Woo. You're gonna see this graph all the time now, and you're gonna be like, this is so easy right now.
Wait, what's gonna happen after?
Oh, did I say that? Did I let that slip?
What's coming?
Lots of good stuff. All right, so you know the drill. I'm gonna still have us do it. The limit as x approaches 3 from the left. Okay, so the most accurate answer, 3 from the left. Yep. The limit as x approaches 3 from the right. Infinity. Okay, the limit as x approaches 3. Now, they both match, so the most accurate answer to put is infinity. Okay, let me show you another one. Let's try this one. Okay, let's break this down into parts. What's the x plus 2? Do you want to try this on your own first? Yeah? Okay, try it on your own, then we'll confer. Okay, what does the x plus 2 do? Left 2. What does the 3 do? Just the 3. We don't care. What does the square do? What does the negative do? Yeah. Okay, then when we do the 3 limits, the limit as x approaches negative 2 from the left, and that's going to be negative infinity. The limit as x approaches negative 2 from the right, and that's going to be negative infinity. And then the limit as x approaches 2, well, since the two sides match, this is also negative infinity. How are we doing so far? So far, so good. And now you'll be able to take, like, look at that. Like, you could take that and you can now, in your mind, be just like Andrew. You can graph that. Okay, well. Well, he's pretty good at the trig and stuff also. That one, I don't know. All right, next we're going to change gears a little bit. Some things that we've talked about, but I want them to be official in our notes, so we have them to look back on. We're going to officially define vertical asymptotes. So we did a lot of this on Friday, but we didn't put this in our notes exactly. And it's going to be the math jargon. We just got to get better at all the technicality. And here's what we'll write. So we'll have lines, and vertical asymptotes are actually a whole vertical line. So that's why we have x equals c. Could be multiple spots, especially with trig. Think about tangent lines. The tangent of x has multiple vertical asymptotes. We have a fraction. The bottom of the fraction would equal 0 at a certain number, but the top would not at a certain number. So we practiced that on Friday. Here's our official definition. And then we're going to put one example of this in our notes so we have that officially. So let's try this. Our function will be x squared plus 2x minus 5. Nope, minus 8. Minus 8. I did. Over x squared minus 4. And so some questions, they're going to say, which we did practice on Friday, find your own points where something's happening and then determine what's going on there. So this is kind of like what we did Friday. So let's factor and see what we get when we factor. That top, we need two numbers that multiply to get negative 8, add or subtract to get 2. What are those numbers? There you go. And then the bottom is a difference of squares. So x plus 2, x minus 2. Okay, now these cancel out. So that would make both the top and the bottom 0. I'll put this here just so we have that as reference. X equals 2. That's removable. That's a whole. But then a negative 2 does not make the top 0. So x equals negative 2. That's non-removable in our vertical asymptote. So we spent some time on this already, but here's just the official part to it. Yeah, Ethan. So you set your term equal to 0. All right. One more thing in this section. We're going to go to and talk about some properties. And last time the properties were very helpful. Like 2x squared minus 3x plus cosine of x minus 7 sine x is continuous. That was very helpful. These will be too, I think. Okay, so properties of infinite limits. There are 3 of them. Oh, actually, I'm going to do something before that one. I'm going to say the limit of f of x as x approaches c is infinity. And then the limit of g of x as x approaches c equals, I'm going to put capital L, and that just means some limit exists. They did L for limit. There is a number. Okay, now here's what they say. The first one is the sum or difference property. And here's what it says. The limit as x approaches c of f of x plus or minus g of x. So we had one before, and what it told us, if you remember, we're allowed to split each of those up and think about them separately. So the limit of f of x is infinity plus or minus the limit of g of x. Okay, now think about this, and this is where it's strange because infinity is kind of an abstract topic. If you take infinity and you add 2 to it, it's still infinity. If you take infinity and you subtract 400 from it, it's still infinity. So when we have an infinite limit and we add or subtract a constant from it, it's still going to be infinity. All right, next one is product. The limit as x approaches c of f of x times g of x. Okay, we also had a property a little bit ago that said we're allowed to look at each of them separately. So the limit of f of x is infinity times the limit of g of x, which is some number L. So if you take infinity and you multiply it by 3, it's still infinity. If you take infinity and you multiply it by 1/4, still infinity. Can you think of anything where that won't work? 0 and negative numbers. So for this to work, L has to be greater than 0. If we take infinity times a negative number, so infinity times -2, it's going to be negative number. So this is when L is less than 0. So you follow the sign of the L is what you do. Now in terms of 0, there's no rule because so many different things happen. So there's no consistent rule for what happens with 0. We have to come up with another way to solve it. So we can do it with these. I'll say this. L equals 0, do something else. Maybe we'll have to graph it or do a table or something like that, but nothing that is always the same for 0. Okay, third property, quotient. So we see this coming. The limit as x approaches c of g of x over f of x. Okay, so again, we're allowed to look at them separately. G of x is L, f of x is infinity. Okay, so we have a number over something that's growing. Okay, so let me give you an example of fractions where this occurs. 1/10, 1/100th, 1/1,000,000th, 1 over a quadrillion. As the bottom keeps getting bigger and bigger, what happens to the value of that fraction? Gets smaller and smaller. And since it's a limit, you might say it's approaching 0. So as we have a number on top and the bottom is infinitely getting bigger, it's approaching 0. All right, let me show you just a couple quick examples with this, just so you can see it in action. Let's try this one. The limit as x approaches 0 of 1 minus 1 over x squared. Actually, let's make that a plus. 1 plus 1 over x squared. Okay, now we're allowed to look at each of them separately. So remember just from like the very first time we did limits, what's the limit of 1? 1. Okay, now this is something we learned today. This is based on the parent function, 1 over x, but now what's it look like, 1 over x squared? Right? 1 over x, but they're both going positive. So what's the limit as x approaches 0? Infinity. Okay, well, if you take infinity and you add 1 to it, it is still infinity. And that's kind of how we're going to work. I think that we'll leave it there. We'll get some more examples going that'll help us, but I think that's a good way to leave that. Any questions you want to recap it, or you want to address something I said? Okay, we're going to stop there. That is officially all we need to do for 1.5. So tomorrow we're going to review 1.4 and 1.5. Wednesday we're going to have a quiz.